In this video, we're going to be continuing our discussion on the energetics of radical halogenation. We're going to take another look at the table we finished up finished up a previous video looking at. And this is a table of bond dissociation enthalpies. And when you look at it, the most obvious trend is that as you go down the periodic table, right? So notice here, like iodine is below bromine, which is below chlorine, which is below fluorine. So when I say go down the periodic table, I mean go down from fluorine towards iodine. So when you go down the periodic table, the HX, so X is just, X denotes any of these halogens. The HX strength decreases. Also, the Rx strength decreases for any given alkyl group. So, say for methane, the CH3F bond is 110. CH3Cl is only 85 kilocalories per mole, and it goes down. Iodine's the weakest here. And the same thing applies for even bigger alkyl groups. So the isopropyl, the secondary isopropyl group's bond, alkyl group bond with fluorine has a DH value of 111. With chlorine, it's 84. With bromine, 71. Iodine, 56. So as you go down the periodic table, that bond gets weaker as well. And the same thing's the case for all of these these Rx bonds. So the bond between the alkyl group and the halogen, as well as the hydrogen halide bonds. And let's see if we can make some argument as to why that is. So when hydrogen bonds to a halogen, you have this small 1s orbital here in hydrogen, and it has to overlap with the outermost p orbital of the halogen. And really, the smaller, the closer in size two things are, the more easily they'll be able to overlap. So let's say draw this a little bit smaller here. So something like this would be the 2p orbital in fluorine, right? In fluorine. But something like this would be the 3p orbital in chlorine. You're adding another shell here, so the orbital is much bigger. It becomes much more difficult to overlap with this small 1s orbital in hydrogen. You go down the periodic table, these orbitals become increasingly large. So I'll say this is the 5p orbital for iodine, and you can see that's very, very difficult for that to overlap with this small 1s orbital in hydrogen, because the closer two things are in size, the easier it is for them to overlap. So that can explain why this HF bond between the hydrogen and the fluorine is stronger than, say, this HI bond, because the 1s orbital of hydrogen more easily overlaps with the 2p orbital in fluorine than it does with the 5p orbital in iodine, because the hydrogen and fluorine are closer matched in size. The overlapping orbitals are closer matched in size. A similar argument can be made for the CX bond, or the RX bond, and that entails a overlap. This R is just this alkyl group, and it's carbon there that bonds to the halogen. And in carbon, you'll have an sp3 hybrid orbital bonding here. And so what that really looks like is looks something like this. I'm just going to draw all the lobes here. you'll have the big lobes, basically the ends of them should be vertices on a tetrahedron. So it looks something like this. It's actually much smaller than this. But it's imagine this, but say like half the size. So orbital, the orbital is not half the size, but if I drew, it's obviously much smaller. But if I drew fluorine this big, say this orbital is about half the size, given that fluorine is this big. So you can see it's fairly small. It'll more easily overlap with fluorine than it would overlap with something bigger, say chlorine, and certainly more easily than it would with a massive 5p orbital of iodine. So that should explain why all the RF bonds are stronger than the RX bonds as you go down the periodic table. You can see the consistent drop in bond strength. Now when you look at this, the X2 bond here, the bond of between fluorine and fluorine, chlorine and chlorine, bromine and bromine, and iodine and iodine, you don't really see much of a trend. It goes up from 38 to 58, but then down to 46 and down to 36. So there doesn't seem to be a consistent trend going down the periodic table. So that doesn't really have an influence on the energetics of radical halogenation. But remember that this HX bond here and the RX bond are the bonds that are formed. So I'll just write HX and RX are formed and RH and XX are broken. When you react a given alkane with any of the halogens, this RH bond is going to be the same in all of the reactions. And we saw this XX bond, there's not really much of a trend here. You know, the fluorine to fluorine's 38, chlorine to chlorine's 58, bromine to bromine's 46, iodine to iodine's 36. So there doesn't seem to be much of a systematic increase or decrease going down the periodic table. But in the bonds that are formed, the HX bond is going to be strongest with fluorine, weakest with iodine. Similarly, the RX bond is also going to be strongest with fluorine. Fluorine's the first column here, and weakest with iodine. And because the HX and RX are formed, what this results in is that so these, when you actually look at the thermodynamics of the reaction, you will have this bond will contribute to a release of energy, as will the formation of these RX bonds here. And the same, but the ones with fluorine are going to be more exothermic than formation of the ones with fluorine are going to be more exothermic than ones with chlorine, and those will be more exothermic than ones with bromine, which in turn will be more exothermic than ones with iodine. So what this amounts to is that radical halogenations with fluorine are the most exothermic. So radical halogenations are most exothermic with fluorine. Let's abbreviate it, exotherm, with fluorine with F, and least exothermic with iodine. And in fact, I'm pretty sure that the reaction with iodine is actually endothermic, so it's not favorable. So we'll actually be taking a look at more examples of these reactions in future videos. And the reactivity of these, so the reaction with fluorine is the most reactive, and with iodine is the least reactive. The reactivity has some implication in terms of selectivity as well, and that selectivity relates to which hydrogen is abstracted. So when you have say something like 2-methylbutane, here, depending on the reactivity, this hydrogen here may be much more likely to be abstracted than this one. So or they may be equally likely. This would still be the most likely to be abstracted, but it wouldn't be all that much more likely than, say, one of these hydrogens. And the reactivity with each of these halogens has implications in terms of the selectivity, but we'll get to that in future videos.